Can you see my screen?
Yes.
Okay. Okay, so let's start. Uh, Hello, everyone. Hello, colleagues. My name is Vladislav Shevlov. I'm a PhD student of National Aerospace University, HAI, and me and my colleagues have prepared this work. The name of it is Availability Markov Models of Complex Equipment with Relearning Diagnostic Means After Detecting Latent Failures. So we will look at motivation, goals, and state of art and objective of our work. Look to our methodology and use case, and proceed to conclusion and discussion section. So diagnostic and monitoring means are important for critical systems in terms of detection, visualization, and decision making. Hidden failures reduce availability of the entire system. But at the same time, intelligent diagnostic and monitoring means can improve visualization, transparency, and control, and thereby increasing this availability of critical systems. Digital twin can be the enabler technology for such intelligent monitoring means, monitoring and diagnostic means, because it allows for real-time monitoring based on machine learning, because of its comprehensive model, and because it becomes a single source of truth. But this work, we will focus more on the modeling part. Uh, so our goals are develop a method to assess availability of critical systems with intelligent monitoring and diagnostics that have this learning capability. Also, we need a method that compares availability of such systems when diagnostics have a learning capability and doesn't have. And finally, we need to develop our basic model that will be used for our use case for simulations and modeling to test our hypothesis and test the behavior of such systems. The reviewed papers mainly propose approaches of predictive maintenance frameworks in complex and critical systems. Also, they propose assessing or improving the availability of critical systems using Markov chain or multi-fragmental Markov chain approaches, but don't consider methods for assessing and modeling of this and modeling how learning capability affects availability of such critical systems. So that's why our objective is to develop a methodology for modeling and simulating critical systems with intelligent diagnostics, meaning with learning capability, to test how that learning capability affects availability of the entire system, and test the following hypothesis. Relearning capability improves error detection of diagnostic means, and however may reduce the availability of the entire system at the beginning, but increases availability in the long run. So here's our methodology. Let's briefly look through the main bullets. So it consists of 5 points. First of all, we need to determine changed parameters. So that means we need to understand what parameters will change in our model through the time of simulation, for example, failure rate or number of repairs. In our case, we will focus on reliability of control parameter. The name of it is D. Secondly, we need to develop a set of basic models. These are Markov chain models, and they describe the behavior of the system, allow us to model system behavior and transition between states. After that, we need to choose at least one model from this set that will be used for modeling. The rest of the models can be used for to formulate recommendations and for further investigations. After that, we need to build a comprehensive multi-fragmental Markov chain model from this basic and abstract basic model. So to build this multi-fragmental model, we already have selected this basic model and change parameters. We also need to define a function that describes how our parameter will change. In our case, it is D parameter, which is reliability of control. Also, we may need cross-fragmental states, but it is optional. And we need to finally create this graph, multi-fragmental graph. And finally, in order to test our hypothesis and analyze results, we need to define key indicators of availability. So in our case, we formulated the following list. So we need steady availability function for three models, for three cases, when diagnostic means have learning capability, doesn't have learning capability, and when diagnostic means are ideal. Also, we need parameter for maximal loss of availability. So that means that we compare a model with learning to the model without learning. So we need to calculate maximal loss. We need to calculate time of this loss. Also, we might need points of minimal availability for model with learning and without learning, and time of transition to stationary availability. So let's see how to build basic models. So basic models reflect the behavior of the system. They are quite abstract. As you can see on the figure 1, this is just a Markov chain model with a few states and transitions. But at the same time, this dashed vertical line separates one main fragment from the rest abstract fragments that should be synthesized when we will build multifragmental model. So we selected basic model 1 for analysis and for simulation because yes, it is quite simple, but at the same time it is illustrative and contains all necessary physics that allow us to test our hypothesis. And let's see the structure of this model. So in table 1, it consists of states, transitions, and parameters. So we can see states like upstate, downstate, hidden failure state, and others. Also transitions like failure rate or recovery rate, or maybe transition to upstate from the learning state rate. And three parameters is probability of failure detection, probability of need in learn after recovery, and in learn after error detection. So yeah, as I said before, we created a couple of more models. We didn't use them for simulation, but they can be used for further investigations. And here you can see that for the same case, different approaches can be used. For example, we added one more state that SDL state, which means that every time when we end up in this state, we will need to transition to the learning state. So this is the only difference, and difference between models is in logic of the transitioning between a hidden error state and how we end up in learning state. But yeah, we will focus on basic model 1. And here you can see on this figure the synthesized multifragmental Markov chain model from the basic model 1. So this model is now comprehensive. It is a graph that we can model and simulate. It consists of 3 fragments, and the last fragments contain only 2 states because it represents an ideal error detection. And that's why we don't need a hidden error state and learning state. And the final proportional step is parameterization ranges. So this table just describes logic under ranges we selected for our simulations for every parameter. So here are details of this physics. And once we're done with all these steps, we are ready to start our simulation. Yes, first of all, we need to describe our, we need to understand where we can simulate our models. We used R language with Markov chain and diagram packages to model Markov chain models and visualize them. Several experiments were conducted to test how changes in different parameters affect key indicators. and every single experiment was done in the scope of 3 cases, and that's why you can see 3 lines on this chart in figure 4. The cases are diagnostic means with training, without training, and when diagnostic means are ideal in terms of error detection. So these 2 tables and this figure represent the basic setup, and basic case. That was the starting point for the rest of experiments. And table 3 represents input parameters. Table 4 represents output or key indicators after the experiment 1 basic setup. And figure 4 represents or visualizes the key indicators. So here you can see that diagnostic means with ideal fail detection has almost the perfect availability. When system is without learning capability, it is worse than the system with learning capability. But at the beginning, you can see this loss in availability. But it is only a basic case. Other cases can vary in its physics. So, for example, table 5 represents 8 more experiments with parameters that we change and main results of the changes. So, meaning how this change affects the whole picture. And for example, you can see that on figure 5, we only changed error detection transition. So it is now much higher, and that's why our losses are not so critical. On the figure 6, you can see that we also set L parameter to the high value. So this parameter is a probability of moving to the learning state after any degradation state. So that means we try to learn almost after every failure, and that's why we end up in stationary state much faster. And finally, interesting case in figure 7 is when availability is when maximal point after learning is almost the same as starting point. So that means that learning gives almost no effect, and in that case, it may be even more profitable to not do this thing. So let's finalize our results. So yes, the model was basic, but at the same time, it still represents basic physics that allow us to test our hypothesis.
Vlad,
Also, yeah.
excuse me, you spent already more than 15 minutes. Please go to the conclusion.
Yeah, it is almost, it is conclusion, yeah. So, yeah, briefly.
This is discussion. Please go to conclusion.
Okay. Yeah. So, diagnostics is one of the key components for critical systems that increases availability. But at the same time, learning capability can even more increase this availability of the entire system. Our experiments confirmed the hypothesis, and that means that almost in all cases, learning capability is profitable. But there are cases when we should avoid this learning. And also, finally, further works will focus on making these models more accurate, investigating practical implementation of how making this diagnostic means intelligent, and to contextualize our methodology in domains like transport or manufacturing. So that's it. Thank you for your attention. Any questions?
Thank you for your presentation. So we are waiting for 1-2 questions. Who will be first with question? Once again, we are waiting for 1, 2 questions. So I have questions. Please show your first slide. First,
Uh,
number one,
First,
number one.
number one, this one, yeah?
Okay, here. So you are talking about diagnostic means, okay? Detect latency. So
Yeah.
what is a, because I stopped you in the discussion, but the most important thing here was your contribution, own contribution with in comparison with the existing one. So what is your contribution? What is your results in comparison with the related work, recent related works in the domain? What is your contribution in comparison?
Mhm. Yeah, okay. Thank you for your question. I have this information on this slide. So yes, the main contribution of this work is not to improve availability, but developing a method that allows to assess how learning.
Excuse me.
Yeah.
You show us state of the arts. I ask you about your results in discussion, probably. What is your contribution in comparison with the related works in the state of the arts table?
Yeah. Okay. I can open
Please
discussion.
open discussion probably
Yeah.
here. What, but here just general phrases. So what is your contribution? Uh, Own contribution. What's your impact in comparison with the existing ones, in comparison with the related work, which
Uh,
you showed in the table?
yes. So the impact is that first of all we confirmed hypothesis that formulated before. So that means that in most of the cases, learning capability in diagnostics is profitable, but there are edge cases, and I added and we added suggestions for these edge cases when learning should be avoided or should be done in a bit different way. For example, when uh, learning is poorly implemented, and because learning state may move the system to the partially unavailable state, the total profit may be too low for making learning.
Excuse me,
Yeah.
it's you said us just general phrases. I asked you about some concrete result, and because you showed table, and probably you do you have some numeric results, like you improve something in comparison with the existing ones?
Yes, I have only the results
Okay,
that.
no, please don't repeat your presentation because you presented already. But what is was your prototype? What is your uh, the closest related work with like objects for comparison? Was it was related work was prototype for your paper?
There are two main related works which assess availability of critical systems
Okay,
based
my
partitioning
question
model.
is, what is the impact your impact, your paper impact in comparison to those two closest related work? What is your impact?
Impact is the following. We formulated cases when learning is profitable and when learning is not profitable, and develop and proved it via simulation and modeling.
Okay, thank you. So, unfortunately, we have no time for other questions. So, and thank you so much.